Okay. Now, first thing I have to tell you on the notes, made a mistake. I wrote day 52 again. But it's really not so bad because we're really just continuing what we were doing yesterday. So you can make it day 52.5 if you don't want to cross something out or whatever. Oh, thanks. Thank you. Okay. Now, on your desk, you have that one page of notes. And then we also, you have the review sheet for the test Wednesday. Why? Every time the class starts. Yeah. And then, but because you guys are probably going to get hit by a lot of tests next week, right? Everybody's Wednesday. Yeah. Well, you can take it earlier if you want. Oh, wait. Did I have to hear all your other problems? Nope. Nope. Didn't. Oh. I'm sorry. I'm in the holiday. Yeah, I'm recording. Yeah. Don't see it. Now we're saying that. All right, finish so we can take a tea. All right. So anyway, because the test is going to be Wednesday, and I know you have a lot to do next week, probably all your teachers want to test you before you go away, I thought, you know what? I'm going to give you the review sheet now. I threw in the answer key. If you don't trust yourself to not look at it, whatever, you can return it to me. I just thought instead of asking everybody separately, do you want to have it now, just file it away and don't look at it until you try it. This way, if you want to get ahead on your studying this weekend, you can look. I just put like every kind of optimization or linearization or related rates problem I could on it, and then I can just choose from those and pick a few to make a test up. So, yeah. Yes. 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 I'll actually help before that. What's that? Yeah, we'll do review on Tuesday. Okay? The people that want to feel better. Okay, so we are going to go back to yesterday's notes. I put one extra problem on with today because in case we can get to the shadow problem, that would be great. But we were on the ladder problem yesterday, right? We got to go through all the, yeah. Well, oh, don't look at that. Don't look at that. Don't look at that. What else? Just doing, yeah, you didn't see it. Okay, yesterday we were talking about taking the derivative with respect to t, which is what you have to do. You want to know at what rate quantities are changing. So if you take the derivative of t with respect to t, you get 1. But if you take the derivative of any other variable with respect to t, you get that derivative, d whatever dt. What? Let's see. Okay. So if you take the derivative of both sides of this equation with respect to t, what would you get on the left side? dv dt. Okay. You can't say that that's 1 because we're taking the derivative with respect to t. What about on the other side? 4ir squared dr dt. Excellent. Very good. That's a key part of solving a related rates problem. After you get a formula, you're going to have to take the derivative of both sides with respect to t. It's always going to be with respect to time, t. Okay, so we're going to go right back to the ladder problem. Okay? Where were we on the ladder problem? We wrote out the Pythagorean theorem? Oh. What? Whoa, not too far. Just. Okay. Okay, so we got a building. Okay, we had a couple windows. That was important. Maybe a door. Yep. What's that? I don't know. I think I am. Are we recording people? Where did it go? Oh, we are. Oh boy, it's going to be a good recording today. There's a lot of bad time. All right, let's see. So, but thank you, because we just got to make sure. So we had a ladder. The ladder was 26 feet. That never changed, so we put the 26 feet right on it. But we said any length that is changing, we're going to put a variable on it. So what did we call this length here? Because as the foot of the ladder slides out, that was going to change to next. And what do we call this distance here? Why? So smart. Right? So variables get labeled. Quantities that vary get labeled with variables. Quantities that are constant get labeled with constants. Then we had to get an equation to relate everybody. And that's when you said Pythagorean theorem, right? So the other thing, wait, I'll write that out, but you had to figure out what derivative they gave and what derivative they're asking for. What was the derivative they gave us? Dx dt. Because x is increasing at a rate of 3 feet per second, you find the derivative in the problem by looking for units that look like a ratio. So we said dx dt was equal to 3 feet per second. And what were they looking for in this problem? dy dt, because they said how fast is the top of the ladder moving down the building. So, good thing I can do this. All right. dy dt, that's what we want to know when x equals 10 feet away from the building. Okay. And that's where we were? Did we take the derivative of both sides with respect to t? Ooh, okay, so at the good part. So, once you know how the quantities x and y are related, you've come up with an equation with those variables in it. Now you take the derivative with respect to t. So, what's the derivative of the left side? 2x. Wait a minute. Yeah, it's with respect to t. It's not with respect to x, so we need a dx dt plus 2y. dy d what? See? Whew. Equals, for the other side, 0. I bet you were thinking 2 times 26 to the foot. No. 0, constant. I don't know about you, but after applying the Pythagorean theorem, I love just to divide both sides by 2. Is that okay with you? Yeah? Okay. Because 0 over 2 is still 0. Let's see. So we have x, dx dt, plus y, dy dt equals 0. 0 over 2 is still 0. So we had a formula. We took the derivative with respect to t. Now our last step, we plug and chug. We plug in what they gave us, and we chug away till we get what we're looking for. We're looking for dy dt, so we got to fill in everything else. What do we put in for x? For x, 10. Okay, but then for dx dt, we're going to put in 3, because that was 3 feet per second or whatever. Oh no. I don't know what to put in for y. I know we got to leave dy dt, but that's what we're looking for. But that means we have to put in something for everything else. At the moment, this ladder's sliding down, and x is 10 feet. At that moment, do we still have a right triangle? Oh yeah. Can we figure out what this missing leg is at the moment when x is 10? Oh yes, we can. Now it is a special right triangle. Does anyone recognize it's a multiple? It's not a 3, 4, 5. There's some other ones though. I also got to do Pythagorean theorem. 5, 12, 13. Oh, it's a thing. 5 squared plus 12 squared equals 13 squared. Right? Oh, so that is a thing. So it's a double. You just double the. So when this is 10, right? What is this side going to be? 24. So that's the quick way to do it. If you can see that, that's great. But for anyone sitting there going, oh my gosh, I don't know what they just did. You just write down 10 squared plus y squared equals 26 squared and do the math. And you figure out what y is that way. That's your punishment. All right. Now, so we filled in everything other than dy dt, so now we can solve for dy dt. What are we going to do? What do we do first? subtract the 30. So we have 24 dy dt equals negative 30. Divide by 24. So dy dt is equal to, reduce that. Something goes into both of those. Negative 5/4. Yeah, 6 goes into both of those. So negative 5/4. Now you always have to give units when you're giving your answer. Y is a length. What is length measured in this problem? Feet. And T stands for time. What's time measured in? Seconds? Okay. So, oh no, why do we get a negative answer? So, because Y is decreasing, right? Yeah, the ladder's going down. So that distance here, Y, is decreasing. So at that moment, the ladder is sliding down. When X is 10 feet away from the base of the building, it's sliding down at a rate of 1.25 feet per second. Scary, right? Oh no, if you were on that ladder, you'd be scared. That's very scary. We could draw the guy in the ladder. Oh well. All right, so ready for another one? We're going to do all the classics. Love the classic problems, like the ladder problems in every single textbook, every calc textbook you can ever find, because it happens a lot. People on ladders and they start sliding out. See, that's how I usually make them. Yep. Yep. You can get to figure, as you're falling, you can figure out how fast you'll be dropping at a particular moment. Oh, wait. Give me, here, I didn't do my erasing right. Don't do about it. Okay, what am I doing? I'm doing this. All right, take a look at the next one. Read the next problem. All right, you read the problem? What's it about if you read the problem? A spherical balloon. All right, guys, draw yourselves a spherical balloon. That's great. That's a great balloon. Put a little hashtag. Now we say, oh my gosh, that's 3D. And then I'm going to give it the whole 3D effect. I think I'm going to ruin it by doing that. But I just want you to get, that's not bad. You know, is there anything, like this balloon's being inflated, is there any place I can put in numbers? Anything staying constant? No, I don't get to put a number on this guy. What length is changing? I had to pick a length, the radius. I mean, technically the diameter is too. We always talk about the radius, though. Yeah. Remind me to keep using a capital R for radius. I tend to go back and forth. Just confusing. All right, so we have this balloon, spherical balloon. It's being inflated with helium at the rate of 100 pi cubic feet per minute. How fast is the balloon's radius increasing? At the instant the radius is 5 feet. Well, we've labeled the only length we can. The radius is increasing. So it's time to figure out what derivative was given and what derivative they're asking for. Find the derivative, given derivative in the problem. Yes, Audrey. All right, let me write that down. So yeah, that has to be a derivative because the units, that's a ratio. It's not just feet or minutes. It's a unit. It's a ratio of units, cubic feet per minute. So somebody's derivative is 100 pi cubic feet per minute. So it's something dt. But what's changing? Where am I in? The r dt. Now, that might be, but I'm just looking at, they never said, they just said it's being inflated with helium at the rate of, so they didn't say something's increasing. Yes, Ellie. Why would you say dv dt? How'd you know it was volume? That's the thing. You see the units here, guys? Cubic feet measures volume. Anytime you have any cubic units of length, that's how you measure volume. What do you measure area in? Square units, like square inches, square feet. That would be your clue. So even though they didn't say the volume of the balloon is increasing at a rate of, you have to know it's the rate at which the volume's changing, and the only way you're going to know it is looking at the units. If it's cubic units, it's volume. All right, let's find out what derivatives they're asking us for. Tell me the name of the derivative we have to find. So we have to find, ooh, I almost went lowercase, dr dt, any particular moment when the radius equals 5 feet. So when r, oops, equals 5 feet. Yeah, no, I keep doing it. I feel like I'm being inconsistent. I have to be consistent with capitalization. Hey, wait a minute. I don't want to confuse the kids over. I'll confuse them with something else. Just not that. Alrighty. All right, so we have dv dt. We want dr dt. That means we need an equation with a v and an r that relates the volume of a sphere to the radius of a sphere. Oh, it's right there. So we're given that the volume of a sphere is 4/3. You've seen this somewhere before, right? Does this look familiar? Oh yeah, it was a dude. That's right. No, I mean, like, have you ever used that? Maybe in geometry? Volume of a sphere? Oh, it was a long time ago? Yeah. Freshman year. You were just a little kid when you saw that. Okay, so we have an equation, volume equals 4/3 pi r cubed, so when we take the derivative with respect to time, we'll have a dv dt and a dr dt. It's great. Then we can plug and chug. So let's take the derivative of both sides with respect to t. Oh, wait, I think you know this. What's dv dt 4 pi r. I'm amazed you guys remembered. Oh, we're done? Oh. dr dt. Now we're talking. So you got the setup, the equation, the derivative. Now's the fun part. Plug and chug. You plug in the stuff that you know, and you solve for what you don't know. What we don't know is the dr dt. So we'll fill in everything else. dv dt was positive 100 pi. Did we ever say it was positive? I don't think I made a point of it. We didn't say it was negative, but I didn't make a point of saying it's positive, because when they give you a derivative, they won't tell you either way. You have to figure it out. How do we know that dv dt is positive? Yeah, because v is increasing. That's how we know that the given derivative is positive 100 pi. If any quantity is increasing, its derivative is positive. Sorry about that. So we're going back. All right, we fill in the dv dt is 100 pi. 4 pi, what are we filling in for the r? 5. Oh, this is fun. It's probably the only time in this class it's going to work out beautifully, the numbers. So yeah, more than that. What do we get for dear? Happy holidays, kids. That was your gift. That's never going to happen again. So we get dr dt is equal to 1, but we always have to give units. So, you know, it has to be the units of the radius over the units of time. So what are the units going to be? Feet. Not cube, because r is the radius, it's a length, so it's only going to be measured in feet. Per minute? Right, so maybe you have a machine and it's inflating it at this constant rate of 100 pi cubic feet per minute. And when the radius is 5 feet, we figured out that it's changing at a rate of 1 foot per minute. You guys have blown up balloons before, right? when you first start blowing it up, you see the radius changing, right? But then as it gets bigger and bigger, what happens to the rate at which the radius increases? It decreases. Let's see if that makes sense. If, look right here, if that rate at which you're blowing up, the dVdt, that's the change of, if you keep that the same, you keep blowing up the same rate, and you make R greater, what's going to happen to the RDT? It's going to decrease. So this is just confirming all your childhood observations. Yeah, when you blow up a balloon and that radius gets larger, it grows, seems like it's changing by it's slower and slower and slower the way it's increasing. The rate at which the radius increases is just slowing down. So if I tried to figure out what's the RDT when R is some other huge number, it's going to be very small. You'll barely notice the change in the radius. You know, the larger the radius gets, as long as you're blowing the air in, you know, at a constant rate. You're putting in whatever number of cubic inches of air per minute. You're not getting tired of decreasing that or whatever. Yeah. All right. So that's the sphere problem. Yeah. But here comes the cone problem. The cone problem. Yeah, don't tell her that there's a special trick with the cone problem. If she missed it, she's never going to get this. So let's try to go quickly. Get this done. Wait, nope. You got to do it again. What? She doesn't know what she's doing.
She's not that smart.
Oh yeah, she could look at this. I wasn't thinking that. Alright, so here.
You should lock the door.
That's good. Could do that. Where's my clear? Oh, there it is. Wow, I really need glasses. Oh, I'm sitting on tape. I know, I gotta try. I'm not really good with that. I don't know how to edit. Okay, now read this one. Water is withdrawn from a conical reservoir. Conical? Does that mean funny? Someone who's conical? Oh. All right. Conical reservoir. Show me what that's going to look like. What do we get? All right, a cone, right? And it says vertex down. So draw a cone, vertex down. It's a reservoir. Maybe it's made in cement. It's holding something. Now, this conical reservoir has an 8-foot diameter. Is that changing? Nope. This is a container. It's holding liquid. So the actual diameter is not going to change. So it's okay if I not changing. And the reservoir is 10 feet deep. Not going to change, right? Nope. All right. Now, water is withdrawn from it. So we have water in this conical reservoir. I need the water marker. All right. Really? That's right, Denise Smart. I got to think of that next time. I don't know if I can learn new tricks. Might be too late. Because earlier today, I thought I could handle the big one, and I went out of the lines, and then the kids didn't get past that. So you know what? I wasted time going back and erasing all the stuff I did out of the line. All right, so here's...
That looks really good.
It does, right?
You're like in the lines. It's neat.
This is why I subbed for an art class today, because of this kind of ability. Too bad Sydney's not here. I would have done something, but I can't. All right, so wait, if I want to go back to the regular marker, I have to go up here. I don't know any other way. Where? Oh, yes, there we go. All right, so here's the surface of my water. That was good, right? Nope. You gotta try to figure it out. So you have water in there, and water is being withdrawn blah, 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 at a constant rate of 5 cubic feet per minute. All right, now wait, you have water, it's dripping out of here. I don't know why. Maybe it's being pulled out by some pipe. I'm just going to have it dripping out here on this. That's sad. I don't know. It's just being, it's just says water is withdrawn. I don't know how it's being withdrawn. But it's a changing. That's why we're using calculus. Now, since the water is being withdrawn, are there any lengths that are changing? Because I need to put variables on those. Like what? Okay. So the diameter of the surface, we don't deal with diameters usually. So we'll do the radius. It is changing though, the diameter. But who wants to say ddt? Nobody wants to say that. All right, so that's changing, the radius of the surface of the water. What else? The water's dripping out, okay? It's height. I say we call that H. Wait, would I put the arrow up to here or up to here? The bottom one? It looks good. No, you do whatever you want. It's the height of the water. But those are, it's almost like I should have done like that. All right, so we've done all our labeling, the constants, the variables. Now we need to figure out what derivative did they give us. Figure that out while I get untangled. Oh, it's in the crevices. You're going to figure out what derivative did they give you, what derivative do they want. I didn't hear it said right once. I heard they gave us the volume, they gave us the V. Oh, nice. So they gave you dVdt. So that 5 cubic feet per minute is the dVdt. And remember with the given derivative, they won't tell you if it's positive or negative. You just got to figure it out. Do you think dVdt, that 5, I should make it keep it positive or make it negative? Negative because, right, volume's decreasing, so the derivative is negative. dVdt is negative. Because the volume is decreasing. That's why I put that there. All right, now we got to figure out how fast is the water level falling when the depth of the water in the reservoir is 6 feet. So what's the height? Okay, so we're trying to figure out something when h is 6 feet. Yeah, I might bug you, like, oh, what is that? How fast is the water level falling? So they're trying to figure out at what rate h is changing, the height of the water. So we're looking for dH dt. So we have dV dt, we want dH dt, right? Okay, so now we need an equation that relates volume of a cone to height of a cone. How nice. Or so nice. Just look and you will find whatever you need. It'll be right there. So the volume of a cone is just 1/3 the volume of a cylinder, right? The volume of a cylinder is area of a circle times height. You take that and multiply it by 1/3, and now you've got the volume of a cone. So, what's that? Oh, I know, my printer said, what? You must have meant P. I don't know. Changed it. Yeah, make that a pi. Here's the thing, though. We're dying to just take the derivative right now. We take the derivative right now. Tell me the derivatives that will result. We'll get a dVdt. The RDT and dHdt. Oh, we don't have R. We don't have the RDT. We don't want the RDT. If we take the derivative right now using the product rule, because these are both variables, right, we'll have to go through the whole product rule, and then we're like, oh, no, we don't have the RDT. We don't want the RDT. So let's avoid that. if we can. So I got to somehow come up with a way to get rid of that r. I have to get another equation and substitute in for the r. Well, we got this picture here. I'm just going to draw a little cross section of it. I'm just going to like pretend that I could slice this thing and just look at half of it. So for the whole container, the diameter was 8, so this would be 4. Well, the diameter of the whole thing was 8, right? So the radius, if I just cut this in half and took a slice, that'd be 4. And what's this whole length here? 10, right? And then inside, we got the water. And it had a R there for that length and H here. If we can figure out an equation with an R and an H in it, we can solve for R in terms of H and substitute and be happy. If only we could see something. You said you saw a right triangle, which was cool. All right, Pythagorean theorem's not going to help us because we don't have anything with the hypotenuse, right? These are both little right triangles, all right? Something about similar triangles. I think it might have if you said that. They are similar. Now, the reason that they're similar, okay, yeah, if the angles are the same, and these are both right angles, they're the same. This angle is the same because it's shared by both of them, right? And these are corresponding angles when kept by transversal. All the angles are the same, so these are similar triangles. Corresponding sides of similar triangles are in proportion. Okay, a proportion is an equation. Well, when you set up that proportion a long time ago, there are different ways you can do it. You just have to be consistent. You have to say blah is to blah is blah is to blah, whatever. All right, so if you go 4 is to 10 in the big one, on the other side it has to be R is H. Yep. Now, that's not the only way to do it. You could have done it another way. You could have said 4 is to R as 10 is to H. I mean, as long as you're consistent. Now, we're trying to solve for R because we want to solve for whatever we want to get rid of. Let's cross multiply. 10R equals 4H. Well, right now we're just trying to solve for R so we can substitute back in before we take the derivative. Over 10. So the radius of this liquid is always 2/5 the height. Now, if you were able to just look at that original picture and see that the radius of the whole reservoir is 2/5 the height, you can just skip all this, you know? If you looked at the original thing and said, oh yeah, 4 is to 10, oh yeah, that's the radius is 2/5 of, so, but if not, you set up the proportion. Okay, so now we can go ahead and get rid of that nasty R. We're going to replace it with 2/5 H. Now we have an equation in terms of V and H, so when we take the derivative, we'll only have the v dt's and the h dt's. It's going to be good. Let's clean it up. It's reset, isn't it? Yeah. So square that out, square the 2/5 H, multiply, get the number in front and tell me what power of H we'll have. Clean it up. What's the fraction out front? If you square the 2/5, multiply by the third. 4/25 times a third. 4/75. pi h cubed. You know you got to wind up with cubic units when you're talking volume. You know it. Okay. Now we can take the derivative with respect to t. Let's go. All right, derivative of the left side. dv dt equals derivative of the other side. Three times 4/75. You could make it 12/75, or you could reduce it. You could just, when you bring down the 3, you could just cancel it with the 3 down there. So 4/25 pi the h dt. We did it. We got the derivative. That's our step 3. Now we're to the fun part. What do we do next? Plug and chug. All right. I forgot these values. -5 for dv dt, and we're putting in 6 for h. -5 equals 4/25 pi 6 squared. This is going to be a fine looking number. That is a handsome number. -5 equals 36 times 4, 144 pi over 25. HDT. We could multiply each side by the reciprocal. -125 over 144 pi. You might get it, if you get it as a decimal, go out 3 places after the decimal. I think it's 0.2 something, but I don't remember. $2.76. Now we do need units. H, that's a length. So what would we measure? What would the numerator of the units be? Feet, and then it's over per minute. So, oh no, it came out negative. Is that all right? Because H is decreasing. That's why the HDT turned out to be negative. Like it? Not bad. I mean, we didn't get to D, the one I put on the paper for today. We'll do that one on Monday, the shadow problem. Excited. The shadow problem. Maybe to prepare for, you can go out this weekend and look at your shadow. See how that works. Yep. Oh, because when we took the derivative, we brought the 3 down. So 3, you could make it 12. Yeah. Yep. Oh, yeah, let's do the summary from yesterday. I actually have it on today's, too. Oh, wait. I have it on today's. I'll just put it in here, because I brought it back thinking I wanted to do that. Okay, we're going to do the summary. How do you know you have a related rates problem? What is the basic characteristic? You're given a derivative, you're given a rate, and you're asked for a rate. You can leave. I'm just going to fill this in. Given a rate, and you're asked for a rate. Basic steps to solve it. You want a diagram, if possible. Label variables. If it, well, quantities that vary with a variable. If they change, any length that change, you want to label with a variable, and quantities that don't change, label with a constant. So if the length doesn't change, you put a number on it. If it does change, you put a variable on it. Step 2. Oh, the other thing in step 1, identify the given derivative and the derivatives they're asking you for. Yeah, I got to put that in step 1. I'll just put it up here. Identify given and requested derivative. your rates. This is a little messy. Sorry about that. Step 2, you need to come up with a formula, an equation that relates the quantities and the numerators of your derivatives. Okay. So you need a formula or an equation to relate the quantities and the numerators of your derivatives. And that's either going to be an area formula, volume formula, Pythagorean theorem, or similar triangles. Then you differentiate each side with respect to t. Differentiate with respect to t. So everything is t. And then finally, 4 is your plug-in side. Plug in the information you know and solve for the derivative you don't know. And that is the Oh, wait. If we find that the rate of change of a quantity is negative, then that quantity is decreasing.